this is now the last little bit of the probability, and it involves independent events. So technically speaking, we've been working with independent events quite a bit when we did our tree diagrams, because the first set of events are independent from the second set of events in tree diagrams. So what we know is if I want a red pen in the first drawer and a green pen in the second drawer, then we multiply it, because the thing is with independent events with the and is we multiply the two events with one another to get the red pen and green pen. So that's basically it with independent events. But let's quickly get a recap on our work that we have done so far. So first off, we started with our addition rule, where we know that with the addition rule, it's given that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So this addition rule is for absolutely everything. There's no exclusions with this addition rule. It counts for absolutely all our calculations in probability. Now we also get the complement of an event. And the complement of an event we use when we are given the probability of not A, or the false or negative side of an event. So we know the probability of not A is 1 minus the probability of A, and vice versa. The probability of A is equal to 1 minus the probability of not A. So whenever you're given the negative side of an event, just subtract it from 1 to get the positive side of the event. Now, with the addition rule, we were also given different types of events. The first type of event we were studying is the mutually exclusive events. Now, what we need to know about mutually exclusive events is if I have a Venn diagram, that these events do not intersect with one another. This is event A, this is event B. There's no and between them. It doesn't say that there's no outliers. There could be outliers, I don't know, but it focuses on the events themselves. So this tells me that the probability of A and B would always equal to 0, because there's no intersection. They are exclusive from one another. So with that said, we can then learn from our addition rule that the probability of A or B, since there's no and, it's just probability of A plus probability of B. We're basically subtracting a 0 at the end, but because there's no and. Then we also get our exhaustive events. Now, exhaustive events are events where there's no outliers. So they could be exclusive, they could be inclusive, that doesn't matter. But what exhaustive events focuses on is the fact that there's absolutely no outliers. All the events take place in all the outcomes take place in the events themselves. So in this case, we know, if that's A and that's B, that the probability of A or B would always equal to 1. It's 100% that if, let's say, you can either take math or math lit, there's no one that is an outlier. You need to take math or math lit. There's no outliers in that case. Now, if I take mutually exclusive events and I add it with exhaustive events, then we get complementary events. Now, a complementary event is an event that is both mutually exclusive and exhaustive. So this is a great example of math or math lit. You can either take math or you can take math lit. You can't take both at the same time, so there's no and you need to take either one of those two, so there's no outliers. So in this case, we know that the probability of A and B is equal to 0, and we also know the probability of A or B is equal to 1. So in this case, if we look at the addition rule, we know probability of A or B is 1 is equal to probability of A plus probability of B. And there's nothing to subtract since the probability of A and B is 0. So that is what we have been doing. Now we're focusing on independent events. Let's give ourselves 3 type of events. So we get A, which is a person has blue eyes. So event A is the probability that all the people that I interviewed, and it includes all the people with blue eyes. Event B is a person younger than 10 years old. And then let's make a last event, event C. The person's height is greater than 1.6 meters. Okay, so there is a definition regarding independent events. It's the probability of the one event is not influenced whether the previous event happens or not. So if we look here, the probability that a person has blue eyes has nothing to do whether the person is younger than 10 years old. These two events are totally independent. The probability that the person is higher than 1.6 meters and has blue eyes, again, those two events don't depend on one another. But the probability that a person's height is greater than 1.6 and the probability that a person is younger than 10 years old, those two events are dependent on one another. Because if a person is younger than 10 years old, it is very rare that they are higher or longer than 1.6 meters. So again, the one event is dependent on the other. So with that said, independent events are events that the one doesn't depend on the other. It is basically maybe taking one of the previous examples that we did with the tree diagrams, where we said the probability of a boy or the gender, the sex of a baby, the probability of a boy being born versus the probability of a girl being born, male or female. The first birth doesn't depend on the second birth, and vice versa. Or the first birth doesn't tell us what the second birth is going to be. So those two events are again independent of one another. And when we have events that are independent of one another, we know that the probability of A and B can be calculated by taking the probability of A and multiplying it with the probability of B. So this is the last calculation that we can include in our formula sheet for independent events. So let's check a few examples. If events A and B are independent and probability of A and probability of B is equal to probability of A 0.4 and probability of B 0.3, determine the probability of A or B and then determine the probability of not A or B. So since these events are independent, we know that we can find the AND of these two events by multiplying the one event with the other. So in this case, if I would like to calculate the probability of A or B, we can use the addition rule. But since we aren't given the probability of A and B, we can go and substitute that little bit with what we know of independent events, that the probability of A and B is the probability of A times the probability of B. So let's substitute. We have 0.4 for probability of A, we have 0.3 for probability of B, and then to get the AND part, we can just multiply these two probabilities with one another. So that would then mean that this answer is 0.58. Type it exactly into the calculator and get an answer. Now when we get mixed questions, say for example question 2 says not A or B. Whenever we get mixed questions, the only way to calculate this is by looking at the Venn diagram. We cannot do it without the use of a Venn diagram. So let's say this is event A, this is event B. The probability of A and B, first, remember we always fill a Venn diagram from the inside outward, is 0.4 times 0.3. That would give us 0.12. Now, since we know that probability of A is 0.4, we already took 0.12 from the 0.4, which means what is left is 0.28. The same with probability of B. We know that this entire circle is 0.3. We already took 0.12 from it. So what is left is 0.18. And then finally, what are the outliers? You have two choices. You can either subtract all these values from 1, since the sample space of a probability Venn diagram will always be out of 1. Or you can take this and just subtract it from 1 again, because this probability of A or B is the sum of A plus B minus A or B. A and B. So this would be 0.42 if you calculate it. Now the question that they are asking is, what's the probability of not A or B? So not A is, if that is a circle of A, we make it dead, which means 0.18 is not A and 0.42 is not A. So not A is red. Then B is everything that's part of the circle of B. So it's 0.12 and 0.18. Now we want red or green or both. That's how the or works. Red or green or both. So in this case, it's the sum of 0.12, 0.18, and 0.42. And this would give us 0.72. So just to recap, if I asked you instead, what's the probability of not A and B? We're looking for the number with a red and green circle at the same time. And this would only be that 0.18. So and is at the same time, or is red or green or both. We're given the probability of A is 0.3, the probability of B is 0.5. Calculate the probability of A or B if A and B are mutually exclusive. Now we know if events are mutually exclusive that the probability of A and B is equal to 0. So if I would like to calculate the probability of A or B, I can use the addition rule by saying the probability of A plus the probability of B. We're not going to be subtracting anything. because what I'm going to be subtracting is just minus 0, minus the probability of A and B. So in this case, the probability of A or B is just adding the two values, and then I get 0.8. Question 2 says, calculate the probability of A or B if these two events are independent. Now, if two events are independent, I can calculate the AND part by multiplying the two events with one another. So probability of A times the probability of B. In this case, it would be 0.3 times 0.5, which would be 0.15. So to calculate the probability of A or B then, we can still use the addition rule, probability of A plus probability of B minus the probability of A and B. Where the probability of A is 0.3, probability of B is 0.5, minus the probability of A and B, which is 0.15. Type that into the calculator, you would get 0.65. So there's a big difference between these events. Mutually exclusive means A and B are not intersecting with one another. Independent means they are intersecting with one another, and to figure out that AND part, we can just multiply the two probabilities with one another. Now, this is brand new. This is called a contingency table. And what it shows is a lot of statistics, basically. It says in a survey, 1,200 cyclists were asked whether or not they have been ever involved in a road accident. And the results are as follows. So what we read here is the total males that were interviewed is 600. And the total females that were interviewed was 600 as well. So 50-50. We see that if I cross male and had an accident, 320 male cyclists had accidents, and 280 cyclists, male cyclists, had no accident. So what we see here is if we add these two together, you should get 600. The same with the females. If I add these two together again, I need to get 600. What we see here at the bottom is 570 people that were interviewed had accidents. 630 people had no accidents. If I add these two again together, I need to get 1,200. And if I add these two together, I need to again get 1,200. So that's how a contingency table works. We focus on, in this case, 4 different events: had accident, no accident, and males that were interviewed and no females that were interviewed. So we are asking, what is the probability of randomly selecting a female cyclist who has not had an accident? So the probability of female and no accident. So let's look. There's female and had no accident. So 350 females out of the 1,200 people that were interviewed had never had an accident before. And if we simplify that, which is not really a requirement in probability, you can leave the fraction as is, it would be 7/24. Now question 2 asks, are the events of being female and having had an accident independent? So we are asked to see, are these events independent? What we know about independent events is the probability of and B is the probability of A times the probability of B. In this case, we need to prove that the probability of A and B is the probability of A times the probability of B. So we cannot just assume it, we need to prove it. So first we can look at what is the probability of a female driver being a cyclist or having an accident. So the probability of female and accident. We can read this just from the graph. A female with an accident is 250 over 1,200. And we can go and put this in decimal form as long as it would possibly give us. And since it's rational, it's just, or it's a recurring fraction, so 0.2083, and that 3 is recurring, but let's just keep it like that. And let's check the probability of being a female times the probability of having an accident. So this doesn't focus on female and accident. We are just trying to see, does this probability of female and accident equal to probability of female times the probability of accident? So the probability of being a female or female that has been interviewed is 600 over 1,200. And the probability of having an accident is 570 over 1,200. So we're not focusing on one single value. We are focusing on what's the probability of a female being interviewed, what is the probability of having had an accident, and that is those figures. So now we can go ahead and calculate that. And in decimal form, again, it's just easier to look at the figures. 0.2375. Now looking at these figures, they are very close to one another. But the thing is, they are not exactly the same. If they were independent, they would be exactly equal to one another. But they are not. So that we can then conclude that these events are not independent. Because the probability of the two events occurring at the same time with the and is not equal to the probability of these two events being multiplied with one another. So it doesn't follow the rule for independent events, so they are not independent. Question D. Events A and B are independent. Determine these two events. Now we did such an example, so what would be great if you actually paused this video here and then you can check the answers. Okay, so hopefully you have already done this question. Let's see. These events are independent, which means that we can use the independent formula to calculate the and. So they are asking us first, what's the probability of A or B? And we can know that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And in this case, we know that the probability of A is 0.2, probability of B is 0.15. And to calculate the probability of A and B, since these events are independent, we can take the probability of A and multiply it with the probability of B, again because these events are independent. You can also do that calculation just on the side alone, if you would like to do that. Type this on a calculator and you get 0.32 as the probability of A or B. Question 2 again is a mixed question. Whenever they ask a false of one and a true of the other, you cannot do this without the use of a Venn diagram, or it's going to take you way longer to do it if you don't use a Venn diagram. So since these events are independent, we know that they are inclusive events, which means there's an AND. To calculate the AND, we just multiply 0.2 of 0.15, multiply these two events with one another, and with this you would get 0.03. So that is the probability of A and B. Since the entire A is 0.2, subtract 0.2 of 0.103, then you would get 0.17. The same with B. Since the entire event B is 0.15, we already took 0.03 from it. It would be 0.12. What is the leftover? What are the outliers? You can either take 1 minus the probability of A or B, or you can take 1 minus 0.17 minus 0.13 minus 0.12, then you would get 0.68. So now, to answer this question, probability of not A or B, we need to look at not A is the orange. So if that is A, make it dead. There's not A, and that value is also not A. B is everything within the circle of B. So we are looking for orange or blue or both. So 0.03, 0.12, and 0.68. The sum of everything would give us 0.83. Okay. Now, a very likely exam type question. Let A and B be two events in a sample space. Suppose the probability of A is 0.4, probability of B is probability of A or B is 0.7, and the probability of B is K. So we don't know what B is. For now, it's an unknown K. And again, they haven't said anything about these events. What they are asking for, find the value of K find the value of K if A and B are mutually exclusive. What do we know about mutually exclusive events? Oh, we know that the probability of A and B is equal to 0. So find the value of K if these two events are mutually exclusive. Now we have the OR, we have A, and we have B in terms of K. So in this case, let's use the addition rule. So we have A or B, we have A, and we have B. And since the AND is 0, we can just subtract 0 or just leave it out. So we know that this part is 0.7. We know A is 0.4. I need to find K. So let's just subtract 0.7 with 0.4, and you would get 0.3 for the value of K. Now, what if these events were, instead of being mutually exclusive, they were independent? If they were independent, I can find the AND part by simply multiplying event A with event B. So again, using our addition rule, probability of A or B is probability of A plus the probability of B minus the probability of A and B. And we know the AND part is just the two probabilities multiplied of one another. So A or B is 0.7, A is 0.4, B is K, minusing the two events multiplied of one another. So 0.4 times K, because I'm following the independent rule. Let's simplify. 0.7 is equal to 0.4 plus K minus 0.4K. 0.4 times K times a negative is 0.4K. So let's take all the numbers to the one side, all the k's to the other side. If I subtract the 0.4 from 0.7, I get 0.3. And then k minus 0.4k is 0.6k. Divide both sides by that 0.6 to get rid of it on the k side. Then we get k is equal to 0.5. So that's the value of B, probability of B, if these two events were independent. Okay, let's check out this one. A survey was conducted with 200 people about their preferred weekend activity. The options were going to the movies, going hiking, or staying in. Now, I would like you to try this one on your own again. So pause this video, try the question, and then come back in a while. Okay, let's see how it went. Question 1 asks, what's the probability that a randomly selected person is female? So the probability of female. Well, there's the female, all the activities, and we interviewed 120 females. So the probability of being female in this case is 120 over the 200 people interviewed. You can either leave it like that, or you can simplify the fraction, and that would be 3 over 5. Question 2. What is the probability of a randomly selected person does not prefer hiking? So this is the hiking people. 75 people said they liked hiking, but we want the not hiking bit. So you can either do the complement rule that says 1 minus the probability of hiking will give me the probability of not hiking, or you can just do probability of not hiking to be 90, which is the probability of people liking movies, 35, which is the amount of people that like staying in, divided again by the amount of people that were interviewed. And if you do this calculation, you would get 5 over 8 as your final answer there. And again, you could have done exactly the same by saying 1, let's do or. Probability of not hiking is 1 minus the probability of someone liking hiking. If you type this again on the calculator, you would get exactly the same, which is again 5 over 8. Now question 3 asks, are the events of being female and staying in independent? If these events were independent, then the probability of being female and staying in would be equal to the probability of being female times the probability of staying in. So we want to see, are these two sides of the independent function or independent calculation, are they going to be equal? If they are equal, then these two events are independent. If they aren't equal, then they are not independent of one another. So the probability of being female and staying in, there's the females that like to stay in, is 25 over 200. Let's take it to decimal form to take a close look at that fraction. In decimal form, it is 0.125. Now, the probability of being female times the probability of staying in. The females is again 120 over 200. And we multiply this with the probability of staying in, which is that 35 over 200. Let's calculate it. And with that, I get 0.105. These two events are not equal to one another. Yes, they differ by 0.02, but they differ. That's the point. So again, not independent. Okay, then we get another type of question. A survey was conducted among 30 people to determine the relationship between the numbers of hours spent practicing a musical instrument per week and whether they passed or failed musical performance assessment. Write down the values of A, B, C, and D. Now, in this case, you need to know how a contingency table works. We know that this total of past the assignment are all these added together. This total again are all these added together. This total is again all those added together. The same with this total, all those added together. So that is how we're going to solve for A, B, and C. We can calculate A by seeing that 2 plus 4 plus A needs to equal to the total of 14. So 2 plus 4 is 6, plus what gives me 14? That would be 8. So I can just substitute A with an 8. Let's look at B. Since I know that A is 8, what is B? Well, B is again the sum of 8 plus 7 because B is in the total column. So 8 plus 7 would give me 15. So now I know B is also 15. How would I calculate C? In this column, there are so many unknowns. Let's look at this row. Okay, with that said, we can see that C should be 6 because 4 plus what is 10? 4 plus 6 is 10. Now we can calculate what D is because 3 plus 6 plus 7 should give me D, and that would give me 16. Or you can work in this column. 14 plus what gives me 30? Because again, 30 is the total amount. 14 plus 16 gives me 30. So now that we know that, let's then check out the questions asked. Calculate the probability that a person randomly chosen from the sample passed the assessment. So passed the assessment, we know 14 people passed the assessment, so 14 over 30. Again, it's your choice whether or not you would like to simplify. Calculate the probability that a randomly chosen person practiced between 5 and 10 hours. Practice hours per week between 5 and 10. We see the total people said 10 over 30 people practiced between 5 and 10 hours. Practice less than 5 hours and passed. Okay, so there's less than 5 hours and they passed. It was only 2 out of the 30 people practiced less than 5 hours and passed. A person failed the assignment and practiced for more than 10 hours. It is 7 out of the 30. Practiced more than 10 hours and failed the assignment. Question 3. Are the events practiced more than 10 hours and passing the assessment independent? Show all needed calculations. So to calculate independency, we need to say the probability of more than 10 hours and passing. We need to get that value. And then we also need to get the value of taking these two events and multiplying them with one another. If these two sides are equal to one another, then the two events would be independent. So let's check what's the probability of practicing more than 10 hours and passing. More than 10 hours and passing, it would be 8/30. And taking that to fraction form, that would be 0.26 if I round 7. Probability of practicing more than 10 hours, is 15/30. Remember, we're taking the entire. We don't care whether they failed or passed. We just want to get the people that practiced more than 10 hours. So 15/30. And we multiply this with the people that passed the assignment, which is 14/30. Calculating that, we get 0.233. There's a major difference in these decimals, so not independent. Are the events passing the assignment or assessment and practicing more than 10 hours mutually exclusive? For events to be mutually exclusive, we know that the probability of passing and the practicing more than 10 hours needs to be 0. So that is what mutually exclusive says. If the probability of passing and practicing more than 10 hours is 0, then they are mutually exclusive. But the probability of passing and practicing more than 10 hours is 8/30. So we can then say the probability of passing and practicing more than 10 hours is 8/30, which is not 0. So, no, not mutually exclusive. Okay. And that's basically that, everyone. That's it for our probability. If you have any questions, you can please message me. Otherwise, guys, thank you so much.